Good morning, everyone. Welcome to EECon 2021. Technical Sessions 2.1, Electronic Systems, Power Electronics and Applications. It's my pleasure to invite the session chairs, Dr. Ranjith Liyanapathirana and Dr. Vidura Jayasooriya to chair this session. Dr. Ranjith Liyanapathirana received BSc Engineering in Electronic and Telecommunication Engineering from University of Moratuwa, and M Engineering and PhD degrees in Electrical Engineering from Memorial University of Newfoundland, Canada. His areas of research interest include wireless communication and sensor networks, biomedical engineering, and structural health monitoring. He is a fellow of the Institution of Engineers, Australia, and a senior member of IEEE. He has supervised 12 PhD students and published over 100. He is a senior lecturer in telecommunication at Western Sydney University of Australia. Dr. Vidura Jayasooriya received BSc Engineering in Electrical and Electronic Engineering from the University of Peradeniya and his PhD degree in Electrical and Computer Engineering from North Dakota State University, USA. His research interests include biomedical instrumentation, biosensors, smart grids, and demand-side management. He has published over 18 refereed articles and possesses a patent too. Currently, he is serving as a senior lecturer in the Department of Electrical and Electronical Engineering at the University of Sri Jayawardenepura. The floor is yours, Dr. Ranjith and Dr. Vidura.
Thank you very much. It's a pleasure to welcome you to this Electronic Systems, Power Electronics and Applications session. Now, people are joining the session, and before starting the technical papers, I would like to acknowledge our teachers, past and present, lecturers, research advisors. We have to thank them for what they have done to make us to contribute to our life. So I want to acknowledge that first. And then I would also like to thank Dr. Vidura Jayasooriya for co-chairing this session, and Professor Karunadasa, who chaired the Power Electronics and Applications track. And also thank the organizing committee, General Chair, Dr. Damayanti, and local organizing chair, Dr. Rasara Samarasinghe, and all organizing members, and of course the other volunteers who are behind the screens. Without them, we cannot run these conferences, IEEE conferences. So thank you all. And we have 17 participants. So I would like to start by listing the papers. So there are 3 papers that we have nominated, that the organizing committee has nominated for best paper awards. The first one is a rectangular pulse current generator for calibration of magnetic field sensor by Ouyang, Liu, and Jin. The second paper is sample entropy analysis of cardiac and respiratory responses during 4 limbs exercise by Bandara and Vijayasiriwardana. And the third paper is hardware and control design of a novel 3-phase grid tie inverter system. The authors are Karunadasa, Savindi, Kumara, and Jayasooriya. So these are the nominated papers. So if you are a student author, please please note that if your paper is not selected as the best paper, don't be discouraged. You all are stars. You have done a very good job by nominating your papers for this session. So let us go to the technical papers. We have 6 papers scheduled in this session. The first one is a rectangular pulse current generator for calibration of magnetic field sensors. Hongzhi Ouyang, Hua Liu, and Xu Jin. Are the authors present here? Any of the authors present here for the paper? Well, until they come, we can probably move to the second paper. The second paper is development of an effective 3D mapping technique for heritage structures by Chanaka Prasad, Ashmini Jeeva Udhyani, Mahinda Alahakoon, WGCW Kumara, Ajmal Hinas, and Julian Thamboo. So I would like to invite the presenting author. Who is the presenting author for this paper?
Hello, sir. I am the presenting author.
Oh, okay.
Udhyani.
All right. Okay. So it's Ashmini Udhyani is going to present the paper, and we can now listen to the recording.
Good afternoon, all of you. I am Ashmini. I am going to present about our research, development of an effective 3D mapping technique for heritage structures. This is the content of this presentation. To generate a 3D map of an existing building, we need measurements. How do we take measurements? In Sri Lanka, we always follow the manual measuring method. People use tapes and build stands to climb higher. This process is very costly because we need large number of people. Even we hired large number of people, taking measurements of a large building is very time consuming. Also, this process is unsafe and the final result may have human errors and not accurate. It is clear that we face several difficulties in 3D mapping a building. Why this process is used all over the world, even it is hard. Let me explain. Our country has a very proud history. The historical monuments all over the country are living evidence for that history. Day by day, little by little, these structures are decaying. For the future restoration processes, it is necessary to have a record of the present state. Set of researchers in Cyprus researched about the use of UAV photogrammetry in documenting a cultural heritage. They chose Asinau Church as their case study. Researchers used a DJI quadcopter for their aerial survey. Around 1,000 images were taken and they were processed using Agisoft Photoscan Professional to create the 3D model. This is the summary of our related work. According to this, it is clear that the world used laser scanners, UAV with cameras, photogrammetry technology in 3D documenting as an alternative to the manual process. Then, why can't we use those solutions? The answer is simply the cost. The 3D laser scanners and commercial drones are very costly. But compared to the cost of using 3D laser scanners, the cost of the commercial drones is low. So, we selected drones and photogrammetry as the most suitable cost-effective solution in this research. So, what is photogrammetry? It is the science of making measurements from photographs. The input to photogrammetry is a collection of photographs, and the output is a 3D model of some real-world object. The first step in photogrammetry process is to collect an image set with overlap. Next step is key point detection, and it can be done using several methods like SIFT, SURF, and ORB. Feature matching is the next step, and after that, homography matrix need to be calculated. Homography matrix relates the coordinates of the same physical point in two images. Then, the parameters can be refined using bundle adjustment and surface reconstruction happen next. We tried this concept behind the photogrammetry process. First, we chose two photographs with a high overlap. Then, key point detection was done by SIFT, and after that we found the more similar features. This was done by brute force matcher. Then the homographic matrix was calculated and finally the two images was aligned using the detected matching features. The result was accurate. As I mentioned earlier, the existing technologies for surveying and documentation of historical buildings in the world are not cost effective to use in Sri Lanka as it is. So, we aim to develop a UAV with suitable photogrammetry technologies for documenting heritage structures in Sri Lanka at a relatively lower cost. We selected hexacopter frame as more suitable frame since it is more stable even in high wind condition and also it can endure high payload. Acusat PhotoScan software was selected as the most suitable photogrammetry software to use. With a carbon fiber frame, this is the drone we developed. With 200-meter maximum flying height and 30-minute flight time, this can easily cover a very large building. Also, it can have a very stable operation in heavy wind conditions. Rather than taking images one by one, we enhanced our drone to fly autonomously in a predefined path and take images with a high overlap. After many researches, we found the best way to capture the images to photogrammetry process. So, in the first step, we fly the drone above the building with 0-degree angle and capture the images. In the second step, we hover the drone 25% above from the initial height. Then, take the images with 30-degree camera angle while circulating around the building. Then, we continue the same step with 45-degree camera angle from the initial height and again with 70-degree angle from 25% below the initial height. Throughout the research, we generated several 3D models. For these processes, we used Intel i7 7th generation laptop with 8GB RAM and 4GB NVIDIA GeForce VGA. This is a fatty field area. We took around 100 images of this to generate the point cloud. We took around 217 images of this house and also generated the point cloud. We selected this temple as our next case study. We took around 100 images of this temple and generated the point cloud. And we use 100 images of this pagoda to generate this point cloud. This point cloud of the building was generated using around 1600 images. This is a final test case. We took around 120 images of this water tower and generated the point cloud. This table shows a comparison between features of the point clouds according to different qualities. In Acusat PhotoScan software, we can select the quality of the point cloud generation process. According to the selected quality, the resolution of the image set changes. In ultra-high setting, software uses the original images. We record the processing time and the number of points in each test case for different qualities. The built-in test case had the highest number of points and the highest processing time since it had the highest number of images. Then we measured the model dimensions. The model dimensions compared with actual dimensions, and finally our improved model had less than 2% error percentage. Our aim was to develop a low-cost 3D mapping technique that is suitable for use in Sri Lanka. This was an application-based research and we analyzed widely used technologies all over the world. A drone which can carry a camera was selected as the best solution. So, we developed a cost-effective and reliable solution which can be easily operated in several conditions. According to our results, we can conclude that our solution is a valid alternative for other high-cost 3D mapping techniques. Using this research as the base study, several applications can be implemented. One is developing a virtual museum. We can make a collection of 3D models in heritage structures all over the country, and it can be used to attract tourist attention in situations like this pandemic. Also, this process can be used to implement virtual reality of heritage structures and also in game developing using real scenarios. We hope to achieve these targets in near future too. These are the references we used in this study. Thank you for your attention.
Okay. Thank you, Ashmini. Do we have any questions for Ashmini from the audience? Well, I have a question. Now, what can you extend this your method? Let us say if we replace the GoPro camera with a LiDAR unit or laser, do you think your methods can be, used?
Yes, sir. I'm Chanaka, sir. I'm also one of team member in this team. So yes, if we have two solutions for that, like 2D LiDAR and a 3D LiDAR. If we use a 3D LiDAR, yes, we can get the same model. But if you use a 2D LiDAR, it will only give a 2D map. So we need to do some modifications to get it to 3D.
Mm-hmm. The following up question is, can we use your method to detect damage? Let us say the water tower, for example. Now, if there is any damage in the water tower, have you been thinking about using it for damage detection?
Yes, sir. This can be used for damage detection.
And are you extending this work towards that area?
Yes, sir. Currently, we are developing this with the National Research and Development Center. So in that stage, we are going to use this for crack analysis and structural analysis too.
Mm-hmm. All right. Okay. All right. Thank you. Any other questions? We have some time left.
Yeah, I also have another question. So regarding the innovative approaches of yours. So other than using this drone here, so what about when it comes to computation and these algorithms? Did you do any developments over there?
Yes, sir. Actually, in the photogrammetry software we used, it used all the images we import to that. So we built a preface to the software that it only detects the images with 60% overlap. It rejects the other images using the feature matching and those kind of things.
Okay.
All right. Okay. So thank you very much. We will go to the next paper, and I will now hand over the session to Dr. Vidura Jayasooriya to continue with paper number 3. Thank you.
Okay. Thank you, Dr. Ranjith Liyanapathirana. So the next what we have is actually the group from University of Moratuwa. So the topic is efficiency enhanced 3-port DC to DC converter for Mppt controlled solar battery systems. The group members are Lasindu, Bopearachchi, Hashan, Supun, Liyanage, Virantha, Haridu, Dasanayake, Mppt, and Sharon Bologna. So who's going to be presenting today the video? So first of all, do we have any of the members from this group? Lasindu, Bopearachchi, Hashan, Supun, Liyanage, Virantha, Haridu, Dasanayake, Mppt, and Sharon Bologna. Okay, seems we don't have them here yet. So we'll move to the next paper, and we'll just see how we'll later take the other groups. Okay, so then we have sample entropy analysis of cardiac and respiratory responses during fall-in exercise. And the group members are Eranga Ellen Bandara and Ravi Vijayasirivaradana from University of Moratuwa. Do we have any of the authors here?
Yes, sir.
Okay. Okay, sure. Okay, so then, so you'll be presenting too, right?
Yes, sir.
Okay, sure. Then we will play the video.
Hello, everyone. Before I begin the presentation, let me introduce myself briefly. My name is Eranga. I'm a research assistant at University of Moratuwa, Sri Lanka. Thanks much for accepting and giving me the opportunity to present my research paper. My research paper topic is sample entropy analysis of cardiac and respiratory responses during fall-in exercise. This is the content of the presentation. First, I'm going to discuss the scope and objectives. After that, I will give a brief introduction to my research area. Next, I will discuss the methodology of the research, including participant selection, test protocol, and data recordings. After that, I will discuss about sample entropy. Finally, I will discuss the results and conclusion. These are the scope and objectives. The scope is to study physiological changes during fall-in exercise and to study the relationship between exercise and fatigue. The objectives are to utilize upper limbs, lower limbs, and all four limbs to perform exercises with the exercise equipment, to carry out exercise stress tests, to record cardiac and respiratory responses, and to analyze sample entropy, heart rate, and respiration rate in order to find relationships between exercise and fatigue. To clearly understand the scope and objectives, I will first give a brief introduction. As we all know, physical exercise involves the contraction of different muscle groups to produce kinetic energy. This kinetic energy gradually decreases with time as a result of muscle fatigue. Therefore, prior identification of muscle fatigue is essential because it helps to achieve prolonged exercise while avoiding injuries. In this research, we used an entropy method called sample entropy to investigate the relationship between exercise and fatigue. First of all, I will explain the methodology of the research. 3 healthy untrained male participants voluntarily participated in this experiment. Their detailed physical demographic characteristics were included in the research paper. The test protocol for this study was based on incremental cycling exercise. Here we have step-by-step increase the workout resistance while maintaining constant pedaling rates. For upper limbs exercise, the pedaling rate was 70 RPM. And for lower limbs exercise, it was 80 RPM. In this experiment, all limbs, lower limbs, and upper limbs exercises were carried out until volitional exhaustion. Next, I will show you the devices we used to record physiological data during the experiment. To record heartbeats, we used a chest strap with a heart rate transmitter. To record respiration signals, we used a thermistor sensor mounted plastic face mask. Both heartbeats and respiration signals were collected in pre, during, and post-exercise stages of the experiment. This figure shows how a participant performs all 4 limbs exercise with the exercise machine. Before explaining the analysis part, I will give a brief introduction to sample entropy. For simplicity, sample entropy can be defined as the negative natural logarithm of the conditional probability that two sequences similar for endpoints remain similar at the next point. A detailed definition of sample entropy can be found in the research paper. The terms M, R, N, A and B are also described in detail in the research paper. After examining several values for these parameters, the most suitable set of values was selected in order to clearly observe the variations during the analysis. In this study, sample entropies of beat-to-beat intervals and breath-to-breath intervals were analyzed. Next, I will discuss the results of the experiment. First, we plotted the statistical data of sample entropies at pre, during and post-exercise states in the same graph for each participant. This figure illustrates the sample entropies variations of RR and BB intervals obtained from the subject 1. According to the graph, the median sample entropy values were increased during exercise when compared to the pre-exercise state. Not only that, but in most cases, the maximum sample entropy was observed during exercise. More statistical measures and linear trendline gradients of each participant are shown in this table. The average statistics shown in this table were calculated by combining the individual statistical parameters of each subject. As you can see, the combined mean, combined standard deviation, and the combined coefficient of variance were increased during exercise when compared to the pre-exercise states. The maximum and the minimum combined mean values were observed during all limbs and upper limbs exercises respectively. This table shows the exercise durations of each subject and the average exercise duration for each type of exercise. The next table shows the gradient values of linear trend lines obtained from the sample entropy variations of RR and BB intervals. As you can see, the average exercise durations and the trend line gradients are varied with the type of exercise. Now we can observe a relationship between trendline gradients and the exercise duration. That is, the trendline gradients of sample entropies are inversely proportional to the exercise duration. This means that the higher the gradients, the shorter the duration of exercise. In this experiment, exercise duration was related to the level of fatigue. Therefore, as we observed here, the level of fatigue can be evaluated by considering the trendline gradients. Furthermore, the relationship between heart rate and breathing rate was also analyzed in this study. As shown in this figure, autocorrelation peaks at 0 suggest not much correlation between pre, during and post-exercise heart rates in every types of exercises. Similar goes for breathing rates as well. Cross-correlation graphs of normalized heart rates and breathing rates demonstrate a very good correlation between heart rates and breathing rates at all pre, during and post-exercise states, indicating maximum Mach 0. These graphs illustrate the variations of heart rate difference and breathing rate difference at all pre, during, and post-exercise states for all limbs exercise, lower limbs exercise, and upper limbs exercise. These graphs are a good indication that we can use voluntary heart rate or breathing rate in normal situations, and hence can use one parameter, most ideally heart rate, for fatigue detection. Now let's review the key points of the presentation. According to the statistics, we observed that sample entropies of RR and BB intervals showed a significant difference between exercise and non-exercise states. Furthermore, we found that linear trendline gradients of sample entropy during exercise are inversely proportional to the exercise duration. Thereby, we suggest that analysis of trendline gradients may be useful in assessing exercise-induced fatigue. In addition, we observed that heart rate or respiration rate could also be used for fatigue detection. Exercise-related fatigue detection using cardiac and respiratory responses will be discussed further in future publications. That is the end of the presentation. Thank you very much for listening to my presentation.
Okay, thank you, Ouyang. So do we have any questions for Ouyang from the audience? Okay. Any questions?
Can I ask a question?
Yes, sure, go ahead.
Now, with the sample entropy, why do they take the natural logarithm? Because I saw the vectors are binary. Why do they take natural logarithm there? Do you know that, or is that convention normally to take the natural logarithm when you compute the entropy?
Sir, I use entropy method due to its simplicity and its real-time data analysis capability. So that's why I use sample entry for the analysis part. And I obtain the results from using that one, but I didn't go deep, didn't went deeply in sample entropy analysis.
All right.
Just for identifying the relationship between exercise and fatigue. That's the objective.
Mm-hmm. Okay, thank you.
Okay, I also have another question. So when you are taking measurements from these three, you had three inputs, right? So when you are taking those inputs, are you actually wearing those the sensors simultaneously, or are you taking measurements in different times? So that how we are maintaining the consistency of the readings. That means if you are taking the, yeah, go ahead.
Yeah, I use both of these sensors simultaneously.
Okay.
Using ESP32 microcontroller.
Mm-hmm.
Then transfer that signals to computer for the analysis part.
Okay, great. Thank you. Are there other questions? Okay, so thank you, Ouyang, again. So we'll move to the next presentation. So it's the cloud movement analysis using Lucas-Kennard method. So it will be presented by Ravindu Tharaka Bandara, Sachini Valigamage, and Lochandaka Ranatunga. All of them are from University of Moratuwa. Do we have them here? Ravindu, Sachini, and Lochandaka?
Yes, sir.
Okay, so we'll go to the video. So we'll see the video and see.
To Honorable Chair, distinguished gathering, all the ladies and gentlemen, a good day to all of you. My research topic is cloud movement analysis using Lucas-Kennard method. First, let's see the breakdown of the presentation. introduction, problem in brief, methodology, overall design, evaluation, conclusion, acknowledgement, references. Introduction. Weather prediction is an essential task as it helps people to manage their work. Predictions with high accuracy can save lives, properties, while having huge impact on country's economy. Cloud movement analysis is a significant process in weather forecasting. Image processing and optical flow techniques can be used to analyze the cloud movement. In here, optical flow is the pattern of apparent motion of objects, edges, and surfaces in a visual scene caused by the relative motion between an observer and the scene. Problem in brief. In the process of weather forecast, a predicted cloud distribution map is helpful in providing the predictions accurately. Cloud motion vectors are needed to generate the cloud map. With the available resources, we cannot directly derive the vector values in numerical form. Weather predictions can be provided by combining ground values and cloud distribution map. By looking at a cloud map, a person with the meteorological knowledge can manually come up with predictions. It can be looking at the density of the cloud. Methodology. Extract satellite cloud images from Meteosat 7 and remove the noise to identify the clouds. Use the cloud area detected images to apply the optical flow algorithm. Cloud movement detection identification, cloud direction identification, evaluation of the results. So as you can see, this is the overall design diagram of the project. As I previously explained, cloud area detected images are used as the input. So these images are used to prepare the dataset. In the third step, it is the noise removal of images. Gaussian filtering was applied to remove the noise on the images. It removed the small cloud clusters and kept only large clusters. This noise removal helped to visualize the image easily. In the next step, canny edge detection algorithm was used to detect the edges of the clouds. It was used since it's a powerful algorithm to identify edges because it used two threshold values to detect the strong and weak edges on the images. In the next step, we apply the Lucas-Canady algorithm. Here, the sequence of images are processed to identify the movement. This algorithm produced a perfect guess of the displacement of neighborhood pixels by considering the changes in intensities which can be explained by the known gradients of image. It assumes movement between two image frames is small within a small time gap. This algorithm is based on brightness constancy assumption, where it states that the pixels do not change the value over time, rather they change pixel location and movement of the location is small. So after applying the algorithm, we can obtain the images with plotted vectors. In the last step, results can be exported to CSV files and it contains x-coordinate, y-coordinate, magnitude and direction of the vector. So these are the cloud area detected grayscale images used as inputs. Images are captured with 30 minutes time interval. So this is the image we obtain after applying the algorithm. And here we have a points track image compared with the figure 1. So this is the image with velocities. So this image is same as the points track image, but this includes the motion vectors. So the size of the arrow represents the magnitude of the vector and the direction of the arrow represents the angle of the vector. Next is the evaluation. Evaluation for this method is based on a behavioral approach. Out of the images, 60 images are used for the evaluation purpose and compared them pairwise. Plotted vector image at a given time was compared with actual image taken after 30 minutes time gap. The top image is the plotted vector image taken at 10 AM and it is compared with this bottom image. It is the actual image taken at 10:30 a.m. So the movement of the clouds can be identified based on a method, and it is explained in the next slide. According to this comparison image, all the defined cloud clusters B, C, and D remain the same in the actual image, but cluster A is not found in the actual image. The reason for this to happen can be the splitting of clusters. Cloud clusters with a definite shape and vectors are considered when conducting the evaluation. Cloud direction identification. So in a cloud cluster, if number of vectors equal to 1, then cloud moves to the same direction of the vector. Else, if vectors are parallel, then clouds move to the same direction as vectors. Else, cloud moves in the direction of the resultant vector. So this based on this method, we evaluate the images. So this is a sample accuracy table we obtain after evaluating the images based on the above method. So in here we have images, test cases, movement, types, truth values, and the accuracy levels. So if we consider the image I01, it has 4 test cases as T1, T2, T3, and T4. And these test cases are identified as the regions as A, B, C, and D. So consider T1 as region B, and by analyzing the direction of the vectors can state that the cloud moves to the left direction, and it is same with the actual image by making the truth value T. Likewise, we can consider T2 and T3 as the regions C and D, and consider consider test case T4 as region A, and by analyzing the direction of the vectors can state that it moves to right direction. When compared with the actual image, this cloud cluster is not found and the truth value is false. So we can calculate the accuracy for the image I01 as 75%. So accordingly, we can calculate the accuracy levels for the rest of the images. So based on these observations, we can come up with some assumptions. Either clouds can be split into smaller particles or can be completely disappear or merge with other cloud particles. So this is the graphical representation of the overall success rates of the vectors. Conclusion. A method has been proposed to calculate the cloud motion vectors using image processing and optical flow algorithms. This method provides a motion vector as the final output with corresponding x coordinate, y coordinate, magnitude of the vector, and direction of the vector by analyzing a series of grayscale satellite cloud images. The model can be further developed to improve the accuracy by finding a method to identify the definite shape of the clouds. So this concludes the presentation. If you have any questions, you can ask now. Thank you.
Yes. Are there any questions from the audience?
Chair, distinguished gathering, all the ladies and gentlemen.
Are there any questions from the audience for Sachini and the group? Okay, it seems we don't have any questions. Dr. Ranjith.
Yeah, I can ask. So normally, if you want to compare different algorithms, you need to have some sort of a standard test image. So if you, are there any test image databases available in the internet, publicly available for you to experiment with?
Yes, sir. We got the image from the Meteosat 7 satellite archive. So our data source was that. So we created our data set by extracting the images from that archive, satellite cloud images.
So do the researchers use that same database?
Actually, we did this project for the Sri Lankan context. So we had discussions with the meteorology department in Sri Lanka, and they didn't have when analyzing the they didn't have separate images for this analyzing the cloud images. So in this satellite, we could extract the images like the Sri Lanka was in the center of that image. So we could analyze the images better by extracting from that data source. That facility was not available with the images available with the meteorology department. So that's why we selected that data source.
So are there any other methods other than the Lucas-Kanade method? And if so, why didn't you compare it with it?
Yes, in some existing approaches, most of them took real-time frequently taken images as the inputs. And in some approaches, they consider like calculating the heights of the cloud. But using satellite images, we couldn't do that. So, in our approach, the source provided images with 30 minutes time interval. So that's why we selected this approach, and the whole project was based on analyzing the satellite images based on image processing techniques.
Okay, thank you.
Okay, I don't have any questions, so we'll go to the next presentation then. So that is the hardware and control design of a novel three-phase grid tie inverter system by Karnadas JP, Sandali Savindi, Nimesha Kumara, and Hemal Jayasooriya. So who are going to present from the group?
Yes, I'm Sandali. I will be presenting.
Okay, Sandali. Okay, so we'll play the video now and take a look at your presentation.
Welcome to our paper presentation. Today I will be presenting on hardware and control design of a novel three-phase grid tie inverter system. Renewable energy-based power generation has become the main focus in the energy field due to the growing concerns of the environmental effects caused by the excessive use of fossil fuels. Renewables are considered as environmentally friendly, clean energy sources. However, there are certain challenges in harnessing the energy from these renewable energy sources to meet the demand. One of the most significant challenges that we come across with the adoption of renewable energy sources in power generation is the cost. To make this renewable energy-based power generation technologies commercially viable, the cost related to the generation of power should be reduced. Renewable energy sources typically produce DC electricity while the conventional grid is alternating current of constant voltage and constant frequency. In order to reduce the cost related to the generation of power, highly efficient power conversion systems are required. With the advancement in technology, the integration of solar photovoltaic systems into the utility grid has increased over the past few years. Inverters and front-end converters are considered as the main components of the systems that integrate solar PV systems with the utility grid. In order to maximize the power generated and to provide efficient power conversion at a reduced cost, these inverters and front-end converters need to have optimal designs. On the other hand, countries like Sri Lanka has limited research and development facilities dedicated to the development of renewable energy-based power generation technologies locally. The industry is mostly dependent on imported technological resources, and there is limited or no local manufacturing of specialized equipment like inverters and front-end converters. Details of the design and control of commercially available inverter designs are also kept as trade secrets. By considering these, our objective is to develop a hardware and control design of a fully controllable source-to-grid complete interconnecting system for renewable energy applications. Our paper focuses on developing a design for a 5 kilowatt 3-phase grid-tie inverter system, including a novel and advanced front-end converter that will extract the maximum power from solar PV panels with improved efficiency and prolonged lifetime. To connect an inverter to the grid, the generator power must comply with certain regulation standards and conditions. As for the literature review, we have identified several international and Sri Lanka standards for the integration of solar photovoltaic systems with the utility grid. Among the international standards, the most widely recognized and used are IEEE 1547 and IEC 61727 standards. These are the requirements for grid interconnection of these power generation sources. By reviewing previous research work, we have identified several limitations of conventional boost converters used in these interconnected systems. The limitations are high duty cycles, which compromises the efficiency, increased switching stresses across the components, high ripple current on active and passive components, and it is required to have a large capacitor to keep the output voltage steady. Owing to these limitations, in our paper, we propose a 4-phase floating interleave boost converter as the front-end converter of the system. In this converter topology, the input voltage source is connected in series with the output capacitors to provide a higher voltage gain. And the same arrangement provides these advantages over the other DC to DC converter topologies. This is the proposed system structure. Moving on to the system design details, to operate the converter in continuous conduction mode, the values of the inductors and capacitors in the 4P-F5BC configuration can be calculated by these equations. For a better operation of the converter, the selection of the inductor values and capacitor values should be higher than the calculated values. Maximum power that can be extracted from PV panels varies with the irradiance and temperature. In order to capture the maximum power under varying weather conditions, we have to use maximum power point tracking techniques. In our paper, we propose perturb and observe algorithm due to its simplicity and ease of implementation. This method periodically increment or decrement the operating voltage of the PV array and measure the instantaneous power output of the PV panel. Depending on the measured instantaneous power, it is determined whether to increment or decrement the operating voltage. This process is continued until the operating point reaches the maximum power point. For the 3-phase voltage source inverter, we have used the indirect current control method as the control mechanism. Controlling sinusoidal or alternating current or voltage quantities is quite difficult. To handle these quantities more conveniently, these AC quantities are transformed to DC quantities using DQ transform method. This is the model that we use to estimate the instantaneous phase angle of the grid voltage. In this figure, omega t is the instantaneous phase angle of VGA with respect to its positive peak. Modeling and simulation part of the project is done using MATLAB Simulink. These are the design parameters of the system. These two tables show the design parameters of the 4P-F5BC design and LCL filter design. This is the overall simulation model that we implemented in MATLAB Simulink. These two figures show the IV and PV characteristics of PV array under varying irradiance, and these two figures show the IV and PV characteristics of the PV array under varying temperature. This is how we implemented the 4P-F5BC model in MATLAB Simulink, and its control design is shown in the other figure. This is how we implemented the perturb and observe algorithm. This model is used to estimate the phase angle of the grid voltage. This figure shows the inverter controller. We have used a monitoring unit to monitor the inverter terminal voltage magnitude and its frequency. If the inverter terminal voltage magnitude or the frequency falls outside the specified ranges, the protection unit will respond to it. These are the two units which monitor the voltage magnitude and its frequency. Moving on to the results and analysis part, we have identified the voltage gain ratio of both the converters, 4PF5DC and conventional boost converter. And when we plot the duty and voltage ratio, we can observe that for the same duty cycle, 4PF5DC has a higher voltage ratio than that of the conventional boost converter. In order to test for the input-output performance of 4PF5DC, we have used this model. The table shows the inductor and capacitor values of the 4PF5DC system. This is the model that we use to test the input and output performance of the conventional boost converter. Inductor and capacitor values are shown in the table. This figure shows the input current of 4PF5DC. It has a ripple percentage of 1% and its ripple frequency is 4 times that of the switching frequency that we have used. This is the input current of the conventional boost converter. It has a ripple percentage around 5.54% and its ripple frequency is almost same as the switching frequency. This figure shows the output voltage of 4PF5DC. It is maintained at 750 and it has ripple percentage around 0.93%. This figure shows the output voltage of conventional boost converter. It is also maintained at 750 volts and the ripple percentage is around 2.4%. By analyzing the results obtained from both the converters, we can observe that 4PF5DC has these advantages. To evaluate the performance of the system under varying irradiance, we have used a curve with step changes in irradiance level. During this whole simulation, we have assumed that the temperature was kept at 25 degrees Celsius. This is to show the performance of the Mppt technique. We have plotted the system power output and the theoretically obtained maximum power output at different irradiance level. By using this figure, we can observe that the system power output is almost same as the maximum theoretically obtained maximum power output at different irradiance levels. This is the variation of inverter current output with varying irradiance. These two graphs shows the grid voltage waveform and inverter output current. Inverter output current is in phase with the grid phase voltage, and it ensures that it operates at unity power factor. This is to show the filter performance. The top graph shows the injected current waveform before the filter and the bottom graph shows the injected current waveform after the filter. These are the results of the monitoring unit. If the inverter terminal voltage magnitude and frequency falls outside the specified ranges, the protection unit will respond to it. We have calculated the total harmonic distortion value. The total harmonic distortion is about 2.18% and we have calculated the total harmonic distortion for different power percentages as well. Moving on to the hardware design, we have selected the IGBT as the switching device. These are the component ratings of the 4PF5DC. This is the gate driver circuit and its gate driver IC. We have selected the C2000 microcontroller for switching signal generation. These are the components of the sensing circuit. Voltage sensors and current sensors are shown in this table. These are the field circuit parameters. Our paper has proposed a hardware and control design of a source to grid complete interconnecting system for solar PV application with these outcomes. Details of the designs and simulations can be used by prospective developers. It has an added flexibility for direct setting of power factor. It has improved efficiency and reduced overall cost as a result of using 4PF5PC at the input stage, and it has improved lifetime of the system due to lesser stress by ripple on input and output capacitors of the DC to DC converter. A hardware implementation of the design is needed to verify the performance fully. These are the references that we have used throughout the presentation. Thank you.
Dali. So,
yeah.
Any questions from the audience? Hello? Okay. Seems I think we don't have any questions. Dr. Ranjith, do you have any questions?
Okay, now if so, how do you know? Is there any intellectual property here that you need to protect? And if so, how do you plan to do it? Have you taken steps to protect any intellectual property that you have in your design?
No, actually,
the answer to this question, it is not yet, of course. It is a design put together locally, but there is no intellectual property aspect was considered so far. We have to do it in the coming future.
Okay. And now, with the standards that they use, you mentioned IEEE and IEC. Are they identical or do they differ much?
Actually, there are some differences, and as we have mentioned, we have particularly focused on the requirements for grid interconnection, as we have mentioned in the presentation in the table. Focusing on those requirements, we have prepared the design. Taken several requirements from both the standards.
So is that the reason why you used 25 degrees centigrade as the ambient temperature?
That's not, since this is a simulation, we have considered it as a constant at 25 degrees Celsius. But as we have presented in our presentation, we have considered that the maximum, the voltage related to the maximum power output is within the range that we have used as the voltage range for the system. So even if we defer the temperature, that range comes to that voltage range. That's right.
Okay, thank you.
Okay, and we have another question from the audience. It came through the chat actually. So Madhushankar is asking, what is the switching frequency used in uninterleaved boost converter?
I guess it's related to the interleaved boost converter that we have presented. In our design, we have used the switching frequency as 20 kilohertz. And that's because that was the switching frequency that has been mostly used in the designs that is available in literature. Is that?
Okay. 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 So I think Madhushankar got the answer. Okay. So do you have any other questions? Okay. Seems we are actually almost running out of the time here, so that we'll check whether we have other group members who didn't present. So do we have any member from the first group, rectangular pulse current generator for calibration of magnetic field sensor? I don't see anyone actually in the audience, so we'll go to the other one. So do we have anyone present from the group efficiency enhanced 3-port DC-DC converter for MPPT controlled solar battery systems?
Yes, sir, we are here.
Okay,
yes, sir.
Sure.
Yeah.
Okay, so then we can play the video so that we can look at your presentation.
Good morning, everybody. I'm here to explain our final year project, Efficiency Enhanced 3-port DC-DC Converter for MPPT controlled solar battery system. Let me give you a brief introduction on our project. As we all know, there's a rapid growth in hybrid energy system. To match different characteristics in energy sources in hybrid energy systems, we need multiple DC-DC converters. Because of this, there are researchers going on making multi-port converters to replace multiple DC-DC converters. But there are issues in storage and getting maximum power. On our research is to overcome these issues and to implement efficiency-enhanced 3-port DC-DC converter for Mppt control solar battery system. Since in Sri Lanka, most of the trend is toward solar, we are trying to build 3-port converter specific to solar battery systems. Our scope is to build Mppt controlled 3-port DC-DC converter for solar battery system with battery management system. In here, we are covering 3 main objectives. First one is to get maximum power from solar panel. Second, to increase voltage gain and employ substitute method to enhance efficiency. Finally, we are trying to reduce battery stress through battery management system. Here you can see block diagram of our project. It contains 3 main parts. First, Mppt solar system. Second, energy storage system. And main 3-port DC-DC converter. Let's go through each part one by one. In solar Mppt systems, we know generally PV panel has low efficiency, which is range of 10 to 20% depending on the material of the manufacturing. Depending on this efficiency, the maximum power point tracking algorithm is designed for the solar PV panel to produce maximum power when solar radiation is available. The duty cycle of the boost converter is adjusted directly by PNO algorithm in order to control operating point of PV panel. The proper operation of developed controller in extracting a maximum power and charging or discharging battery effectively is investigated under standard test condition of environment. To design boost converter, we are following these parameters. Input voltage range is 25 to 30 volt. Normal output voltage is 48 to 50 volt. Maximum output current is 5 ampere. And here you can see a proposed DC-DC converter with Mppt solar system. Here you can see a key waveform of the boost converter of the Mppt system when maximum irradiation occurs. Our converter operates in 3 main modes. First one is solar power is more than the demand power. Then solar PV produce power to the output as well as charge the battery. Second, when solar power is not enough to produce the output power, then solar and battery combinedly produce output power. Third mode, when there is no solar power, battery system itself produces the output power needed. We use coupled inductor techniques to increase voltage gain, and we use a coupled active clamp circuit to provide soft switching condition and to mitigate leakage inductance effect. In system like this, there are many changing variables such as level of irradiation, temperature, and battery state of charging. To achieve steady and optimum level of power and to reduce DC error and to provide fast response to sudden changes, we need good control topology. In here, we use a discrete PWM controller. Here you can see ripples in the battery current in case of we are not using battery management system. This is the state of most of the researchers out there. We need to control and limit the battery current in order to assure safe operation and the better performances. To achieve this 2-stage bidirectional converter with current control is used. Charging or discharging mode will be depending on the battery voltage. Here you can see two transient deviations in load voltage. The first one is occurs when solar power is greater than the load power. When solar power is high, the additional energy is transferred to the battery. Therefore, the converter operation mode is changed with ESS charging mode to discharging mode. Second, when the solar power is less than the load power. When solar power is less, the diffusion power is supplied by the battery. Hence, again, the converter operation mode is changed from which is a charging mode to discharging mode. Those two sudden change of the operating modes are represented by these graphs. These are the substituting conditions results that we took in ESS charging mode. These are the substituting conditions that we took in the ESS discharging mode. As you can see, in both modes, we achieve substituting conditions. As our solar input voltage range from 25 to 30 volt, and we boost it up to 48 volt by MPPT control boost converter in our system. When there's adequate solar, then it tracks the maximum power point and keep it constant voltage until the solar power became less. We are able to reduce ripple in battery voltage from 0.09 to 0.02, which is less than the recommended ripple value by the manufacturer. On the other hand, we can reduce the maximum charging voltage from 26.9 volt to 25.83 volt. It costs to enhance the battery lifetime and the performances. This shows the battery current in charging and discharging process according to the solar variation. You can witness that the battery current is varying from positive to negative and vice versa due to charge and operation mode with respect to available solar radiation. As can be shown, even though the initial in the transition period, it took much higher current, in the rest of the time period, the maximum discharging current is less than 5 ampere. On the other hand, the developed controller charges battery bank with the minimum value of charging current of 1.7 ampere. During this stage of the charging process, power of battery is minimum because of the minimum charging current. Battery current ripple is 2%. It also less than the recommended ripple percentage of battery current. This graph illustrates the efficiency of MPPT solar system with respect to the solar radiation. Our design system has average tracking efficiency of 96.3 over the given value of the radiation, which means it can extract the 96% of the maximum power of the solar PV, which is given to the 3-port converter as input. This graph illustrates the efficiency of MPPT solar system with respect to the solar radiation. Our design system has average tracking efficiency of 96.3. When there's no solar power, then the batteries transfer its power with 95.24 efficiency. When solar radiation is available, then it has average value of 92.97 overall efficiency. Here you can see design parameters of our project, inductor values, capacitor values, frequency, and so on. Here is a comparison of our project with the existing solutions. As you can see, the existing solutions, they have efficiency of 87%, 85%, 80%, and so on. So our solution is better than most of these solutions. Conclusion is we capable of achieving MPPT high conversion ratio in multiple operation modes, and we provide a substituting condition, and also we design battery management system to reduce ripple current. So that's it. Thank you.
Okay. Thank you, Hashan. So, do we have any questions from the audience to Hashan?
Hello. My name is Mppt. Congratulations on a good study and a good presentation. One or two quick questions. When you say efficiency, it's the efficiency of the converter. Is that right? But not the entire converter, battery, inverter system.
Yes. The only in the three-port converter part.
Then secondly, is the converter adaptable in case there is reverse power flow, that by which I mean basically ability for the battery to be charged from the grid. So that power direction will be reversed. Has the control system got the ability to be flexible to do that also?
Yes, power flow can flow in the both directions. So it's possible, because when the solar power is high, and even there's a current pass from the grid part, it can be go to the battery, and battery can be charged.
Right. Thank you.
Okay. Any other questions from the audience? Okay, it seems not. Dr. Ranjith, any question you have?
No, I don't think so.
Okay. So yeah, in that case, I think we are done presenting all the presentations that we had today. Unfortunately, the first group from the rectangular pulse current generator, they were not available, even though they were selected for the, they were actually nominated for the best paper award. I think, so this is the end of the presentations for today then. So before leaving, so if you guys can please turn on your videos, we can take a screenshot so that we can see who presented, who were present today. Okay. Seems I guess we are the only guys who are going to turn on cameras, I guess. So we'll take the screenshot now.
Okay, thank you very much for joining the session. Before leaving, I would like to take this opportunity to thank Dr. Ranjith Liyanapathirana and Dr. Vidura Jayasooriya to make this event a success. And I hope time schedule was they didn't properly aware of the time in Sri Lanka. The Chinese paper, the rectangular pulse current generator. So we are hoping if they are willing to join later, we are hoping to take maybe after the workshop session if they want to present. So we will let you know in any case if we are going to do that. Right? Okay. Thank you so much again for making this event success. And we have another events lined up after the lunchtime, like the keynote session and the workshop. And we would like to invite you for the concluding ceremony as well. All right. So thank you for joining. See you in other sessions. Bye.
Thank you. Bye-bye.